Today I want to rework how strings work. So now that I added bytes to my language Plum, I think strings should actually not be kind of a built-in type, kind of magically provided by the language. And instead, strings should just be defined in the standard library as, I don't know, an array of bytes. Not quite like this though, because then every array of bytes is automatically a string. And I think I don't want that. But instead I want strings to be valid UTF-8 strings. So I think this should actually just be a struct that then contains a member called UTF-8 bytes, which is an array byte. And then every struct with a field UTF-8 bytes, which is an array of bytes, is considered a string, which is fair, I think. It will also not have concat strings from this built-ins package. We actually don't use any built-ins at all. Yeah. All right, so what do we want to import? I think we'll need, hang on, let me change the tab size to 2. I think we'll need array, first of all. We'll need bytes. Yeah, and for now let's not support joining strings. I'll add that later on. Yeah. For now let's just look at the string type. To be clear, I still want this. Still want to support string literals in the code. Like this should at compile time just be converted into a struct of UTF-8 bytes of an array, like that should still work. All right, so I think this is fine. Let's maybe write a little function that just returns a string and make that work. And then we'll go from there. So let's say that the main function will return a string. Oh well, crazy that we haven't done that yet. Yeah. Oh, hang on, what? Try to use call string array with 1 argument, but it needs 0. Oh, I think because the import is wrong. I mean, yeah, imports need to be checked. That's also another issue. But yeah. Yeah. So string shouldn't actually be a type. So in the in the egg compiler stage, the first one after just the syntactic stuff, we'll remove the string operations. We'll kind of remove the, where's that? The string. I mean, yeah, having a literal for strings in here is still reasonable, I think. Yeah. I'm not sure how we convert to the egg. I think here we need to look at the types. Yeah, and string is not something special. Yeah, there is no built-in type string, basically. And really where's that type? Yeah, type string is just a struct. With a member named UTF-8 bytes, which is going to be an array. So I have this type array somewhere here, I think. Oh yeah, here, type array. an array of bytes. Yeah. That's really what a string is. So let's see how that works. Okay, I'm not sure about concat strings actually. Let's try to implement concat strings in the language itself, just to see if that works. So I think for arrays, we will have a more general function for concatenating two arrays. Concatenating an array A and an array B is going to result in an array of the same type. And what that's going to do is it just does a generate array, calls that the built-in function with an int, the length, which will be a.len plus b.len, len being this function for getting the length of an array, which we'll just call the built-in array len function. Okay, so we want to create an array with, the length kind of doubled. And how to generate items, the item and index. The way that's going to work is we check if the index is less than a.len. Yeah. If it is, then we'll just get the item from A. So we'll do a.get from that index. If it isn't, then we'll do b.get from the index minus a.len. Yeah, get the item from the B array. Boom, then we've generated an array that we've kind of copied some of the items from one array, some of the items from the other. Yeah. All right. So then in the string, we can actually have a concat function, like a plus operator maybe even, of some string and another string that returns a string, and that's just gonna be concat of a dot UTF-8 bytes and b dot UTF-8 bytes. Hang on, that's going to give us an array of bytes, and then we'll need to rewrap that into a struct. Like that. Making this a string. Okay. Yeah, that fails in the same place. So in here, we can actually simplify code because we no longer have, oh, I already removed that. Yeah, but in here we can no longer need to handle that. Pretty cool. Then concat strings and the lookup function. No longer need that. Yeah, that doesn't even need to have a type signature. Yeah, then act to yogurt. In the yogurt built-ins, we also don't need this kind of array built in. And when converting the egg to the yogurt, we also don't need to handle concatenation. Yeah, then next stage is the pudding. Again, pudding built in concat strings. Don't need that anymore. And yogurt to pudding, concat strings, no longer needed. Then next compiler stage, pudding to pesto. Let's actually look into the pesto. Here the types are all like very primitive already. We only have bytes and ints, and pointers, structs and enums. So yeah, compare ints. Oh, hang on. Yeah, we already don't have concat strings thing. I kind of gave up at this point, trying to implement that. Because I knew that I wanted to create arrays and kind of implement strings in the standard library. So pudding to pesto. Yeah, this, no need for that. All right, that's pretty cool. Actually compiles. Let's see where that fails. Yeah, that's what I expected. Okay, but it does fail in the plum code. That is nice. So yeah, concat, we need to import that. Concat of an array of t and another array of t. Oh yeah, in the main playground file, we'll also need to import string. Huh. Yeah, and then an array. This needs the comparison function from ints. Also the minus function. So we have plus, we have minus. All right. String to pesto. So if we have a string literal in the code, we need to think about how to handle that. How do we handle, I wanted to say array literals, but I don't have array literals, so yeah, I guess we'll just emit code for allocating memory, copying the string there, stuff like that. Yeah, so this is, I know. First of all, builder.malloc pesto, let's see. Oh, we have new buffer. That is actually, yeah, that's what we want, new buffer. Of pesto new buffer, which takes an item type and a length. Yeah, and this is what this does as well. It takes an item type, which is going to be pesto type dot byte, and the length is just going to be the string length. Oh, hang on. There's something runtime known that represents the string length, so we need to wrap that in a pesto expression. And that gives us a buffer. Then we want to store an item into that buffer. mean, I could just have, expressions in here, like store the first character of the string, first byte of the string into index 0, store the second one into index 1 of the buffer, and just emit lots of instructions that copy the individual bytes in there. But I feel like that's, having kind of string or byte constants in your code is something that I want to be efficient, and that I want to not just have that be efficient, but also efficiently encode that in the bytecode. If your code has a byte constant or a string constant of length 100, I want the bytecode encoding of that to be roughly 100 plus some overhead, sure. But I want that to grow kind of with that, and not have a full instruction containing an 8-byte index and the item and an opcode. So kind of multiplying that with 10 or something, just to, or even more. Yeah. So I think I want a new bytecode instruction actually. Again, yet another instruction. So I want, let's go into the ground empty thing. Yeah. I already have a variable with instructions, such as the jump table, where we have a single byte that encodes how many jump targets there are. And then there are 8 bytes per jump target. Yeah. So I think I'll add some sort of store n instruction, some sort of data instruction. So something that starts with D. And the question is what? We have malloc, we have free, we have store 1 at 8, we have load 1 at 8. I think I'm gonna add some sort of store n. Oh yeah, and the encoding of that is actually n literal, I don't know. Actually gonna be first a byte. Or 8 bytes. I think 8 bytes. Yeah. 1, 2, 3, 4. 1, 2, 3, 4. The x indicates the length of the byte literal. Stop literal bytes. Yeah, after the first 9 bytes, there are x bytes. Yeah. So the store literal bytes instruction pops an address. And stores the literal bytes to that address. And the X indicates this instruction directly contains byte literal to be stored in memory. The bytes to be stored in immediate is that. No, yeah. The number of bytes. After the first 9 bytes, there are X bytes. Yeah, I think that's fine. Okay, so that is D6. Let's implement that in the VM, but hang on, first of all, let's just compile to that and then figure stuff out from there. So store literal bytes. To support that, I think in the ground we'll need some sort of store literal bytes. I mean, hang on, first add that up here. Yeah, that makes sense. Store literal bytes, and that just takes a slice of bytes. All right. Then store literal bytes with some bytes. It's gonna print store literal bytes and then the bytes afterwards. So for every byte in the bytes, it just prints like byte dot. I think there's like a radix function, radix 16, yeah. And a space before that. Yeah, so we have the hex bytes after that. All right, then now we come to encoding that instruction. There we just first of all push a D6. And then we do, well, we have the bytes here. Is that like push bytes? Does that work? Oh, hang on. And the literal. Well. Oh, is there a push all? I think so. That works. Alright, doesn't change anything about this one though. So in the pudding to pesto, I think we'll need something similar in the pesto. You know, loading, freeing, storing a single buffer item. store bytes, perhaps. Pesto store buffer bytes. Assumes a buffer of bytes. Yeah. And you can't even specify a position or something, it's just fill the buffer with that. And to be honest, it's only used for strings, so store buffer bytes. Then in the builder, we will add a new function for that. Store buffer item, also store buffer bytes. Yeah, the item type is just, don't need that. Store buffer bytes, buffer and bytes. All right. First of all, in here, we can now do builder.store buffer bytes. In the buffer, please store the string bytes. I think that's a function. Data and len. Ah, yeah, this works. Store buffer bytes, alright. And then we want to wrap that into a string, which is a struct that contains an array of bytes. So first we need to create an array. That is going to be buffer.struct, containing a reference to the buffer, a start index, which is 0 in our case, a length, which will be a compile time known string length, and then given that array, we then create the actual string. So buffer dot string, buffer dot struct, yeah, with UTF-8 bytes being that array. That is pretty cool. Okay, this case evaluates to nothing, but previous case is to IDs. Evaluates to nothing. I think that's just out of, out of touch with the code base. The error sometimes happens in Martinez. All right, so pesto to waffle. What do we do here? Oh, I think in the waffle we also need a concept of that. Yeah. So if we have store bytes, store buffer item, basically store buffer bytes with this store, then we'll do that. Or at least something like that. We'll have a store. Is that correct? Hang on. Nope. We'll have a waffle store bytes. Yeah, where do we want to store them to? Well, just the index is 0. We do want to skip the first 16 bytes though. And what do we want to store? Well, the bytes. Of course, waffle store bytes doesn't exist. So let's change that. In here, we'll need, oh, look at that, store multiple. We don't even, do we use store multiple? I think I kind of abandoned that at some point. Case, case, case. This is only in this case for optimizing. Okay, optimizing doesn't introduce that. Okay, we do have waffle store multiple, so. Yeah, no, never used. So let's instead change this to waffle store bytes. And it's gonna take a pointer. Yeah, and then literal bytes. Kind of crazy that we don't, that we keep these bytes around so deep into the compiler pipeline. You know, all the, like everything else is kind of turned into waffle expressions and so on, but bytes, well, we still keep the raw bytes around here. So in here we do emit waffle store bytes, store bytes, which will take a pointer and bytes. Just like that. That's not a thing apparently, which makes sense because in here change that store multiple to store bytes. Here as well, takes a pointer and it has bytes, which is just a slice of bytes. All right. Yeah, optimization stuff doesn't work, and also printing, probably. Let's fix that. So store bytes. We'll actually print the pointer and then just the bytes, I guess. Like that. Yeah, all right. With the annotation though, so gotta put the annotation in there, which looks like, oh, we do have an indentation already. That is clean. So just indentation and then store bytes. And we can even merge these here. Cool. So in the optimization stuff, a lot of stuff doesn't work yet because we now have store multiple, which really is just store bytes, which has only as a pointer. At least it's simpler than before. And that's in here, that is in the pre-shake when we need to adjust the code store multiple. Is that pure? No, store bytes isn't pure either. Only have the pointer to worry about here. That is quite clean. Alright, we do have nest though, so store bytes counting references, counts the references of some ID in the pointer, and that's it. And down here we'll try to nest the local variable in there. Yeah. Then we do store bytes. All right. Same thing. It's literally the same thing. And optimize. Can we copy store bytes? Nope. Store multiple waffle to ground. Okay. Yeah. Here we probably switch over the no. Probably have store multiple in here. Yeah. So what we do here is we compute the pointer. So the stack is this. And then this. Don't need that. Don't need that. Yeah, we don't need to batch things and no. We do that way simpler now. Way simpler. Because we can just do builder dot what is it? Like store bytes of those bytes. And that's it. There were no definitions named store bytes. Okay. Or is it like store literal bytes? Sure. I'm fine with that. Although, I mean, store bytes is a pretty cool name for that. Yeah. Yeah, let's do that. And then we have builder.pop of the padding before the pointer. Alright. Yeah, don't need care about this one. I mean, we literally just need that. That is quite simple. Store bytes just aligns the stack. For a pointer, we compile the pointer, we store bytes, we pop. So in this builder, we'll need a store. Is there like a store literal bytes? No, there is not. Huh. Let's add that, store bytes. Just takes bytes. Yeah, no, it's called literal bytes, but I'm gonna change that to just store bytes. And it just pops an address, stores the bytes there, and that's that. So, alright. So then in the ground, let's rename this to just store bytes. That is so cool. Alright. And then let's change that description here as well. Amazing. Oh, okay, so some memory address leaked. Oh, yeah, that is actually true. Very true. Wow, but we calculated, we created ground. That's quite cool. Let's just look at that. There's quite the thing here. So we push 1 0, which if I believe 1 2 3 4 5 6 7 8 9 10 11 12 13. Hello world is 13 bytes. Okay, sure. So what we do here is we push a 16 for some reason. Then we push 0D, which is what? Mm. $13. The length of hello world. Okay. Then we push a 1. We multiply these two, 13 and 1, because I think the 13 is the length of the buffer, and 1 is the size of a single byte in the string. So multiplying these gives us 13 bytes for the hello world. And then we add the 16 for the reference count and the length, which will be stored at the beginning of the buffer on the heap. Alright, that seems pretty cool. So then we do C1, which I'm not sure, it pushes a single byte, the 8, which is the alignment of that allocation. And then it does D0, aka malloc. So this right here allocates exactly enough memory to store a reference count, 8 bytes, then the length of the string, another 8 bytes, and then the string itself. And it just pushes that address onto the stack. So on the stack now we have the argument to the main function, which we won't use at all. And then we have the address of some buffer, of some memory that is large enough to hold the buffer containing hello world. Then we do C4, pushing something that was previously on the stack at offset 0, aka the top of the stack gets pushed again. So we have that address there 2 times now. Then we push a 1 to the stack. So we have address and then the 1, and then D3. We store that into the memory. Okay, the first 8 bytes, the first integer, is now a 1. That's the reference count of the string. Then we store, and that also consumes the address and the reference count of 1, that D3 here. So then we push the address again, copy that again to the stack, and we push an 8 there. Okay. Oh, I see. We add those to give us kind of a memory address into the memory plus 8, kind of skipping the reference count that we've already written. Then we push on the stack D3, the length of our string, and then we store that length into the memory at near the base of address of the memory plus 8. So now in memory we just have a 1 in the beginning for the reference count and then the length of the string. And now what we do is we push that same string address again. We push 16, add those to get a pointer to after the reference count and the length. And then we do this newly created D6 instruction, which actually wants to store some bytes in memory. Oh, and this is, oh, I see. Yeah, some stuff is not working here, which is totally fair, because this misses the length of the bytes here, the encoding. It just says D6 and then immediately the bytes come. But the VM doesn't know how big the stored thing should be. Yeah, this part right here, the axis, they are missing. So in the waffle to ground, hang on, just in the ground, I guess. Yeah, in the ground, in the 2 bytes function. Yeah, we shouldn't just push the bytes directly, but we should push little endian bytes of the length. Yeah, that is important. Making that, running that. Still fails. But let's look at the hex dump again. Okay, so after computing the address where we want to store things, we now store bytes, 13 bytes to be exact, and then here come the 13 bytes directly in the bytecode. So we store hello world to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Okay, yeah, we've stored hello world there. Then we push the address again from the stack. Then we, what's that, C2 pushes a literal, oh, I see. Yeah, we've kind of filled the buffer and initialized that. But now we want to wrap that into a string. So we push the address to the stack, we push the string length to the stack, and the start, I guess, which is 0. And in that order, because struct fields are sorted alphabetically, so first we have the buffer with B, aka the address, then the length with L, and then the S, which is start. Yeah. And then, what do we do here? We keep the top
18 in decimal would be
24. Yeah, we keep those 24 bytes consisting of the address, the length, and the start, aka the string. We keep that, and we pop the 16 bytes below, aka the address that we had before and the argument to the main function. Then we return with just that string. Whew, okay, so the bytecode is correct.
Now this still fails for some reason.
It fails in malloc. Oh, I see. It says unreachable opcode. And then kind of while handling that, memory gets leaked, which is, I guess, sure. Yeah. Let's fix that. Let's support the opcode. So in the VM, I want to support a new opcode, D6. ABCD 6. Which is going to be store bytes. How do other opcodes work, like push? Oh, it says bytecode dot read end and so on. Okay, yeah, that makes sense. So what we want to do is bytecode dot we want to read the length, which is going to be bytecode dot read int. And then we allocate a buffer for that. Oh. No, we don't want to allocate something. We'll just do read bytes, which is something we still need to add here with a length as a usize. So an int cast to a usize. Those will be the bytes. Yeah, then we pop the address from the data stack. We'll have a pointer here. And casting the address to a usize, then taking a pointer from that int. And then storing something there, which will be like this. So I think we'll do mem copy with a destination being the pointer and the source being the bytes. And this will not work, but I want to see the error, yeah. So first of all, read bytes in bytecode. We do have read byte, we have get int at some offset, interesting, we have read int. Then we also want read bytes. Let's even move that up here. Yeah, read bytes, self and length is a usize, and that just does, well, self.program at the current offset, hang on, at self.ip, yeah, dot something, and then with the length, that is some slice of bytes, all right, and then we do self.ip plus equals that length, and we return the bytes. All right. Yeah. So then in here we can, like this should work, read bytes of that length, giving us a slice of bytes. Not sure why that says 6, well, let's see. Yeah, memcopy doesn't work, that's, oh, I see. Down here we still claim that we return, down here? Yeah, we claim that we return an I64 when really we just return a buffer to U8, to const8. Yeah. Alright, the pointer doesn't work though. Okay, so I have an int, a usize, and I want to convert that to a slice. How does that work? Let's maybe look into malloc, because I think that does something similar, maybe? Heap. Okay, yeah, we have an address. Oh, but that's just a pointer or something. Okay, yeah. Oh, look at this. Not sure what the star means. But this does seem to me like it takes this address and it casts that into a memory buffer of U8s. All right. Yeah, not sure about the alignment. I think we don't need any alignment, so alignment of 1 by default. Copy to some pointer in 1.6. That is outdated. Expected usize, found that, okay. But we can int past that. Well, okay, let's say this has to be a usize. we don't need to do that. And there. Okay. Okay, nice. Well, let's try this again. Oh, I think we still need to do zig build. Yeah. Nope. Oh, okay. Ah, I see. I see. So it ran the program. The program outputted something. Not what I expected it would. I think. Oh, maybe it is. Yeah. Okay, let's see. 1, 2, 3, 4. 1, 2, 3, 4. This looks like a pointer into memory. Look at that. It's the same memory that leaks later on. Like flipped around for little endian and stuff like that. But yeah, 7, 2, C6, D1, FE, and then zeros. Okay, so we have a pointer into memory. And then we have, look at that, a length. And then we have an offset. This is a string. Our program returned a string. That is pretty cool. Yeah, and I mean, part of doing this kind of low-level, interfacing with code, programs just returning some bytes, means that in the host program, aka in Zig, we need to know how to interpret those bytes, and that's something that we need to. This data that's returned that's not self-descriptive. We need to bring that to the table. We as developers. So I think let's say that the main function should always return a string for now. Currently it just returned an int, now it returns a string, and then the Zig code will just assume that it does, and yeah, then do stuff. So in the main code, we are running the program with a 5, sure. Then we ran the program, boom, we have some output. Assuming the output is a string. Yeah. Is a plum string, specifically. Get plum string content, maybe. So this is some string that we won't touch, and we will return the underlying string content. Hell yeah. Oh, even better, let's create a type for that. Plum string is really just a struct that kind of mirrors the string struct on the on the plum side, which will be just something with UTF-8 bytes, which will be a plum array of some type of bytes. Yeah, hell yeah. Just a plum. Implement code that understands the memory layout and so on of the plum data structures, so they can interoperate with Zig code, and we can print that string in Zig. So we'll have a function plum array that takes an item type, which is gonna be a type actually. And then that just returns a struct, because an array is really just a struct that contains a pointer, a buffer, which will be a pointer into memory. Yeah. It will have a start field, which is going to be usize, and it has a length, which is also a usize. Then a plum byte is just a U8. Alright, and this returns a type. Oh yeah, the item type is not even used. That is true. Can I just ignore that like this? Oh, no, hang on. Yeah, I think these plum data structures, they have from bytes functions, where you pass in bytes and you get back that same, an instance of that data structure. So in the case of a string, because that's just an array of UTF-8 bytes, well, that is the same as, you know, returning a struct with a field UTF-8 bytes, where the value is, well, plum array of plum byte dot from bytes. Hell yeah. And also this always has a size in bytes or something like that. So this is 24. Yeah, unused function parameter. Let's call it size and alignment, sure. Yeah, and here we can kind of we should assert that. Yeah. And it should have the size, actually. Yeah, okay. So it's just that many bytes. And then a plum array is quite similar actually. Also has a size, which is 24, and alignment, which is 8. And then it has a from bytes function. Well, let's maybe put these up there. I think that's a bit more elegant. Kind of more according to Zig convention. So, yeah, creating an array from a set of bytes. Yeah, the way that works is it basically just returns a struct with a size, with a buffer. There's gonna be bytes, well, the first 8 bytes, then a start. There's gonna be, first there was the length, I think. So this length goes from 8 to 16, and then the start goes from 16 to 24, like that. Yeah. And this, let's also wrap that. That's just going to be a struct containing the actual value. And it's going to have a size of 1, an alignment of 1, and a function for converting bytes into that. We're saying this is just a single byte. All right. Yeah, one level of structness too much. Oh, now one to less. Yeah, that's it. All right. So you might wonder why do this complicated dance of having a byte wrapper around a byte that also has a size and alignment and so on. The cool thing is, when you do it this way, you can actually pass the plum byte in here. And you can kind of duck type this. You can say, I want this item type. For arrays, I also want a way of getting an item. And that returns an item type. Look at that. Let's call it item, maybe in uppercase, because that's usually for Zig types the way to go. It's going to return an item, and the way it does that is by, well, by checking the item size. Okay, no, I think I actually need another type, the plum buffer. Also generic over an item, and that, let's copy this, but it's really not that much that similar, because really this just is a struct with a pointer. Yeah. You can create that from 8 bytes, but just, the pointer is an pointer to you eats. I mean, sure, yeah. Something like that. And for a buffer, you can also get an item at an index. The way that works is it it calculates the item size. And then just assumes that on this item type there exists a size constant. And then it can actually calculate the stride size as the item size. There is no such thing as rounded up to multiple of, I assume. Let's just go with that and write it to doing here. Yeah. And then what it does is, if you want to get an item at an index, we can just, that's a const, we can just get the pointer, add 16, I don't quite know what to do then. Pointer plus 16. Yeah, that's the base of the items. And then we're gonna add the index times, let's call this just stride size, that's fine. The index times the stride size. Kind of dereference that. Like getting the bytes at that position of the item size. And then we do item dot from bytes. Something like that. Yeah. Now this won't work because this is just very unsafe C stuff. Yeah, so here this will actually not just be that, this will be on the other hand, I mean, array is actually the built-in type. Yeah, let's not have this kind of wrapper plum buffer type. Let's just have this in the array directly. I think that's totally fair. Yeah, and then getting something from an array. But then again, this does make sense semantically, I think. Yeah, let's just turn this into a plum buffer of the item type. Hell yeah. Well, which means that you should be able to do this. And here. Yeah. And this is not a usize, this is really like a plum int, I guess. I want the native endianness. I mean, I know it's little, but still feels not super clean. What is it? Font stuff. Okay. Anyways, we have this. This is a plum int. Plum int. Not allowed between container fields. I don't know what to do about that. Well, yeah, getting something at an index from an array actually just gets it from the buffer. So this does need a self parameter. Which then does self.buffer.get at the index plus self.size dot value where there are no container fields after this. Field after declarations here. Function. I don't get it. Don't get it. Field after decorations here. Why is there a field? This is compile time known. Why is this? Oh, because fun is not a thing. Oh, come on. That. Okay. I guess. That is a confusing error message. Expected semicolon after declaration. Yeah, because this is actually a function. Yeah, that's it. Oh, okay, and now I also get error as well. That actually makes sense. Whoa, it's almost usable. All right. Yeah, plum buffer. So let's see. Use of undeclared identifier pointer. That is true. Get needs first of all a self. And then here we do self dot pointer. Stuff like that. Okay, that worked. That is cool. What? That worked? That's amazing. Let's see. Assuming the output is a plum string. And then we say string is plum string dot from bytes output. Yeah, then we print that string, and let's say string has a nice format function here. Let's say write, I guess. I like format. How is that? Oh, that's like a default format thing. Format, I think. Yeah, let's maybe Google how to do. Is it font? Formatting. Look at that. Nope. Yeah. This is what I want. Some sort of format function that takes a string and a format thing and it writes something, and what it does is it just prints the individual characters. So for 0 to self.utf8bytes.len. Hell yeah. Yeah, print those. So we do self.utf8bytes.get at that index, giving us a character, sorry, a plum byte. And then what we do is we do writer.print that byte like so. Alright, and this should allow us to write strings. So what's going on here? We have a string, oh, but we don't use that because we don't print that. Alright, from bytes. Expected a pointer. Yeah, let's. Can I like just dereference that? Does that work? Seems like it does. 77. Huh. Hang on, a plum int. Oh yeah, that's actually I64 internally. Yeah, and then we have plum buffer, we have plum array. Yeah, this is an I64, which makes sense. We just cast that here. Alright. Expected integer or vector from plum. Oh yeah, this has a value internally. Okay, yeah, for plum byte, that is true. The byte also has a value. That is true. Let's add a try in there. Alright, so 94, we do pointer from int. Oh, I see, now we get the errors because now we're actually using that code, or trying to use that code. Well. Let's see, expected type usize. Pointer from int. Yeah, let's do standard and then read int, I guess. Just from bytes. Please read that into the usize. Yeah, with little endian coding, I guess. Expected pointer type found plum buffer. Main 94 in here. Oh, I see. Yeah, this really should go into the buffer, because here we just do plum buffer. Yeah, of the item type. Create that from our bytes. Nice, nice. And then this is where that error probably occurs, where we need to read that into a usize first. Okay, expected type something, found something else. That is true in line 94. And these are really cool error messages, to be honest. You know, where we have this, we need an 8-byte array, but we have a 24-byte array. That is cool. I found a pointer. I mean, I could just pass pointers around here. I think, like, if indexing by default just returns a pointer to that thing. Yeah, I guess let's do that. Then, you know, just say that this just needs to be, what was the type? Pointer of const size. And this should be from int, from bytes, same here, like that. Yeah, and this is really a pointer, so is this, and so is this. Sure. No field named size. Get something. I know where to start. Yeah. type, yeah. Cast that into the usize. Sure. Value of type main plum byte is ignored. Like 101. Oh yeah, I'm gonna return that. Yeah. This is where a lot of things go wrong, so let's see. Because let's just say that the pointer is a usize, you know? Just like that. And then in here we'll actually say, and we take self.pointer, which is a usize, we add 16, we add the index times the stride size, boom. It's an item pointer. Well, yeah. And that's a pointer to, we don't know the size of U8, I think. Yeah. What? Actually compiles. Let's see. Okay, still. Oh, look at that. Up what's that world? What? That is so cool. We can successfully parse strings. And not just strings, like everything. This is, I mean, yeah, just strings, but this is written in a way so that I can easily extend this to other types as well. I can, I don't know, create a function that returns a plum, that returns an array of ints, and then I just create a plum array of, you know, plum ints, and oh, that is nice. Actually, though, I think I'm gonna add a new file for these. So in the, yeah, in here, let's add, or add a new file. Yeah, called plum.zig. And this contains plum specific stuff, like, you know, strings, arrays, buffers, so on. And let's also rename these, drop the prefix, because this is its own module now, so this is quite clear, I think. Hell yeah. Also reorder these, have the byte first, then the int maybe. No, first the fundamental types. Yeah, then string. And then a buffer. Yeah, buffer, then array, and then string. Nice. because this still leaks memory, I think we'll actually need to implement dupe and drop functions for these, because the interface between Plum and Zig is this very, not rigid, but very well specified memory layout. And the Plum code knows how to work with that. The Plum code knows how to work with these data structures, how to dupe them, how to drop them, how to, kind of interpret those bytes. But the Zig code not as much. Now, from bytes we did that. We can interpret strings now, we can interpret arrays. But in order to have nice interoperability with Zig, which actually I think that would be really cool. I think Zig is a really good fit for that, because this entire comp timeness makes it possible to have consistent, to kind of do stuff like we do in the buffer or the array in here. That we just say, well, this buffer actually accepts another type, and then it'll take the size and alignment of that type and stuff like that, in order to implement this these functions. Yeah. So I think I'll keep this, but add even more functions here. Add dupe and drop and so on. And in here I'll just import Plum. That is import Plum. .zig. And then this is a Plum string. Thing. How this works? Nope, does not. String is not marked pub. True. These need to be public, as do the from bytes things right here. And I guess also the values. Never mind, they are automatically pub, maybe. Don't know about that. I mean, buffer is more of an internal implementation detail, so let's not export that on the array. Yeah, size is not marked pub. And line 53. Yeah, true. All right. And now let's add dupe and drop functions. That's crazy. So dupe. No, it doesn't really do anything. Yeah, no. Nothing to see here. Drop also doesn't do anything. Same for ints. Dupe and drop doesn't really do anything. For buffers though, well, dupe and drop does something. Duping a buffer is actually just you're getting, like we have the pointer, which is and we do self.pointer, cast that to a pointer to an int ref count, and then we say, oh, hang on. And then we do ref count is ref count +1. Oh, and this is a usize. Amazing. Dropping a value does the same thing, except decrementing that. And then it also checks if the ref count is 0, then we need to free this. Oh. I think free also needs to be there. Maybe? Not sure. No, probably not. Let's just have ref count in there. Okay, if ref count equals 0, then, well, what we do is we iterate over the items. For 0 to self dot. We get that wrong. That is self dot pointer +8. That is a pointer to a usize, and then for 0 to len, we just do self.get add that item, and we drop that item. Yeah, drop the contained items. That makes sense. Yeah. Then for array, well, we just do keep the buffer to start and the len, and very similar for drop. For string, quite similar actually. Alright, yeah. And then in the main function we can just say string.drop, and this will free the string because it has reference count of 1, and yeah. Hopefully. Nope. Still leaking memory. Yeah, let's make sure this worked. Oh, yeah. Yeah, we docked the string. Oh, oh, I know why. In the buffer, yeah, if the reference count is 0, then we just free the individual items, but we'll also need to drop the memory here. So we'll need to do... Ooh. We need the allocator, I think. So that we can free that memory. Yeah. And this needs the memory bytes. So these will be this will be something. This will be self.pointer. Interpreted as a pointer to an unknown number of U8s. And then from that pointer we take 16 plus, well, len times stride size. Let's do this differently. Let's say pointer from int that is supposed to be a pointer to a usize, and then dot star, so that we have a usize directly. Then we don't need to do that. Yeah. All right. Yeah, then we free those bytes. Yeah, so drop also needs an allocator. Makes sense. All right. Yeah, and then in the main function we also need to pass in the allocator. Member function expected, 1 argument found 0. Hmm. Oh no. What's going on there? No idea what's going on there. What? That doesn't tell me anything. Come on. Because of union field pointer, well, field int is active. What does that even mean? Does that happen because some of this code? Yeah, apparently. But not this one. Right, and not this one. No, just because of the allocator stuff in the end, probably. Yeah. Okay, so freeing these bytes doesn't work for some reason. Oh, because bytes is U8. That is... oh, I see. Yeah, that's more like it. Alright, that builds at least. Whoa. What's going on here? Allocation alignment 8 does not match free alignment 1. Yeah. This is, I mean, buffers are always aligned to 8 bytes right now. That's just the way it is. And it works without leaking memory. And over time, you know, making this interop between Zig and Plum better is also, it should be doable, I think. You're just defining types, defining dupe and drop functions for those types. I mean, for most types, like array, you know, array is like a user-defined type in the standard library. And that's obvious. It just contains the fields of the corresponding types in Zig. Contains size and alignment, which could also be computed, theoretically. Creating something from bytes, yeah. You can auto-implement most of this stuff, I believe. Yeah, and then getting something, sure. Yeah. That is really cool. I feel tempted to do more with comp time here. To just have some, you know, basically have the primitive types like byte and int and buffer, but then have, you know, I guess array as well, yeah. But then just have struct as a function. It then takes a list of fields and their types, and then this does the memory layouting in a similar way to what we do in the Plum compiler, and it implements the dupe and the rob functions and the from bytes and so on. So you can really just focus on the main part. But yeah, I don't know, that's maybe too crazy. Alright.
Yeah, is there something else I wanted to do?
I don't really think so. No. No. Nope. Yeah, I think, I mean, strings work. That's pretty cool. So I guess it works. That's it for this video, and see you in the next one. Bye.